Dear students, in this video, we are going to discuss an important concept of orthogonal projections, which is central piece in many applications of machine learning. Now, when we talk about data sets or real world data sets are often high dimensional and they pose greater challenge in visualization. For example, if we are given a one-dimensional data which we can plot along the line, or two-dimensional data which we can plot on a paper, or even three-dimensional data with that we can view from perspective and try to visualize, visualization is still possible and it gives us greater insights that how our data looks like. However, in many real world problems, specifically in the context of earth system sciences, there is no way we are going to get simpler data sets on our plate, and we have to collect high dimensional data sets from the field. However, most of the dimensions in these high dimensional data sets would be redundant, and hence lot of information would be, or the meaningful information would be contained in a few dimensions. And let us say that we have n dimensions in our original data set. We want to go towards m dimensions where n is greater than m, or maybe n is much greater than m, and we want to project data from n to m using some projection rules. And these projection rules should have an objective, and that objective states that wherever we do the projection of vector x, which is represented in some n dimensional vector space, to the transformed mu xu, and this is the m dimensional vector space, the difference between x vector and mu xu should be minimized. And when we are talking about this distance, we are essentially talking about the norms. So our objective becomes that we have original x vector, we have its projection on some lower dimensional vector space, and that difference between original and projection should be minimized. And whenever we are talking about norms, we are typically talking about L2 norm. Also, we know that whenever we have a vector x, we have another vector on which we want, and another line on which we want to transform it. So our pi xu would be somewhere here once the projection happens. And if we have the closing side of this triangle, that would be essentially the difference of these two vectors from simple vector algebra. So this would be equal to x vector minus pi xu vector. Also, we know that if this has to be the shortest distance, because we want to minimize it, and in this setting, for this length to be minimized, this angle has to be the 90-degree, such that we can achieve this minimization condition. Hence, we can really leverage the orthogonality of vectors that we learned in last videos to identify the best direction to project, or in fact, once we know the direction, best magnitude of projection can be typically inferred as long as we apply this condition of orthogonality. So now if this vector is represented as a b vector, and this vector that I am now highlighting in brown, it represents the vector on which we want to project. So this b vector should be orthogonal to x minus mu xu vector as evident from this figure. And we know that whenever we are talking about orthogonality, we are essentially talking about that the inner product of two vectors of interest should be equal to 0. Hence we can write this as x vector minus xu vector, which we are saying, or pi xu vector, which we are saying is the transformed x vector, and its dot product with b vector should be equal to 0. So we will specifically talk about dot product, but right now it could be any inner product which we learned in our previous videos. Now, since inner product is a bilinear mapping, we can clearly write this as inner product of x and b minus inner product of pi xu and b. Also, this should be equal to 0. This complete subtraction should be equal to 0. Also, this b vector and x and pi xu vector, they are collinear because that's how we are projecting. So we can safely say that we can always write pi xu as some linear combination of b vector, because if you scale up or scale down this b vector, you can always get to this particular projection because they are collinear or they are lying along the same line. So when we substitute this, our expression reduces to xb, their inner product, minus lambda b comma b, their inner product, and this has to be equal to 0, which implies that lambda is equal to inner product of xb divided by b comma b. And we know that if we take inner product of the two same vectors, we are basically talking about square of the norm, which in this case can be written as b square or b norm square, and this can be written as bx. And now whenever we said that whenever we are talking about the inner product, one of the simplest case of inner product is dot product. Hence, if we use dot product to represent our inner product, we can simplify this lambda as b transpose x upon b norm of b and its square. And it's easy to say, if norm of b equal to 1, this lambda is simply given by b transform x. So once we learn this lambda, we can always multiply this lambda by b and we can determine what is our projected x vector, and hence we can always write this as lambda times b equal to, we just determined that this lambda is xb upon b square and multiplied by b vector, which in case of dot product is b transpose xb and norm of b, putting vectors wherever necessary. Also, we can compute the length of pi x or the projected length, which would be simply lambda b, and we learned that since this in case of norms, this lambda can come out and this would be lambda times norm of b vector. Hence our projection is of length modulus lambda or absolute value of lambda times the length of b. Now we can also write it in expanded form that mod of pi xu is equal to b transpose x upon norm square multiplied by b. And if we look at this thing carefully, we learned that if we have a dot product divided by the individual products, we are essentially talking about the cosine of angle, and hence we can write this as cosine of omega and x, where this is the angle between original vector and vector on which we want to project. So we are basically taking AB cos theta as the dot product or the projections that we are very much familiar of. So basically, if we have a vector A and we want to project on B and we know this theta, so the best projection in that case would be A times cos theta on B, and this is what we have typically learned in high school. But now another important question arises, that why we are talking about this in a typical machine learning course. Now when we talk about approaches like linear regression, we know that there are so many points here, and idea is to find a generalized linear model that can sort of represent the variance of all these lines. Even in that case, what we are doing is we are essentially taking the orthogonal projections along the line for which we want to determine the slope and intercept, but we set up the problem in a way that the distance or orthogonal projection of all the points that we are using to find our regression relationship is y minus y hat is minimized, and we try to identify the line such that this holds true for on an average. If there are n number of points, the average error is minimized. Similarly, PCA is pure application of projections. However, when we will go to PCA, we will talk about a very specific theorem which we call as the Gram-Schmidt orthogonalization, which totally relies, as the name suggests, on orthogonal projections, and that will help us determine the principal components or the projected values once we identify that along what directions we want to take our projections, and this will help us also reduce the dimensionality of data sets. Also, some of the recent approaches in deep learning, for example, autoencoders. Autoencoders also use the orthogonal projections to reduce the data dimensionality. And we will not go into autoencoders per se, but if you are interested to go into the math, you would find that similar expressions that we developed here also generalized there.